Yes, welcome to our second lesson of ideal solutions, and in this lesson here we are still building up the concept of ideal and versus non-ideal, and here specifically I want to talk about ideal solution. In the previous lesson we ended by looking at the characteristics of an ideal solution, and we said if we know the characteristics then we can answer someone who tells us to explain the term ideal solution. So how do we explain the term ideal solution? When we're explaining this term ideal solution, we have now to embed all the characteristics of an ideal solution. So we shall say that this is a solution, this is a miscible mixture in which the cohesive forces, or we can say this is a miscible mixture in which the magnitude of the cohesive forces of attraction between the pure components, is equal to the magnitude of the adhesive forces of attraction, between the components of the mixture, Now you realize that was our definition, and we must now go ahead because we are trying to explain. We can now go ahead and say that in this solution, there is no change in expected volume when the two components are mixed. Why do we talk of there is no change in expected volume? It means there is no contraction in volume or expansion in volume. What are we meaning here? It is possible that sometimes you get 50 cubic centimeters of liquid A and you add 50 cubic centimeters of liquid B, and then your expectation, what you expect, is 100 cubic centimeters. But it is possible for this final volume to be less than 100 cubic centimeters or to be greater than 100 cubic centimeters. So you find that you get 50, add 50, and then you get 98 cubic centimeters. So if you get a volume less than what you expect, then we say there has been a contraction in volume. If we get a volume, maybe 102, then there has been expansion in volume. So we are saying that if the mixture is ideal, there is no change in expected volume of the mixture that we are getting. So there is no expansion, there is no contraction in volume. Then another thing, we are saying there is no heat change. There is no heat change. There is no heat change. That is, heat is not given out, heat is not absorbed. When this mixture is being formed, there is no heat change on formation of this mixture. On formation of this mixture. Therefore, the mixture obeys what we call Raoult's law. Raoult's law of dilute solutions. Raoult's law of dilute solutions. So this is an explanation which we will normally carry around 3 marks or 2 marks depending on the interest of the examiner. However, the explanation embeds all the characteristics of an ideal solution. The definition simply looks at the magnitude of cohesive forces of attraction being equal to the adhesive forces of attraction. So now, we are ended by saying that therefore, because of those characteristics, the solution will obey Raoult's law of dilute solutions. Let's look at Raoult's law of dilute solutions. So, how can we now look at Raoult's law of dilute solutions? So we can have Raoult's law. This is Raoult's law of dilute, or we can even say Raoult's law of solutions. Raoult's law of solutions. Now, something to note before we state this law is that we have previously looked at Raoult's law somewhere in colligative properties. And Raoult's law we looked at in colligative properties. We said it equals Raoult's law of relative lowering of vapor pressure. Sometimes we call it Raoult's law of vapor pressure. Now what we are looking at here is Raoult's law of ideal solutions, or Raoult's law of solutions. And this should not be confused with Raoult's law of vapor pressure. So question is that require this are very specific. Normally part B, if the first question is saying state Raoult's law, part B would be on a calculation relating to the law that you are required to state. Sometimes they are even very specific. They will tell you state Raoult's law of ideal solutions. State Raoult's law of solutions. We shouldn't confuse this one with Raoult's law of relative lowering of vapor pressure. So what does Raoult's law state? Raoult's law of solutions states that the vapor pressure of any volatile component of an ideal solution is normally equal to the vapor pressure of the pure component multiplied by the multiplied by the mole fraction of that component in the mixture. Sometimes we simply say that it says that the product, that the partial vapor pressure of any volatile component is the product. So we can state it in the way the word multiplication can substitute the word product. So we can state here and say that this states that the partial vapor pressure of a volatile component of an ideal solution is equal equal to the product, product is the same as multiplication, is equal to the product of the vapor pressure of the pure component, product of the vapor pressure of the pure component, and vapor pressure of the pure component, and the mole fraction of that component, in the mixture. So this law, of course, just like any other law, is governed by temperature. So we can say at a given temperature, because these compositions can keep changing with temperature. So this is what we call Raoult's law. And if this is Raoult's law, we could put a mathematical interpretation of what we are saying. But let's first emphasize a few things. We are saying that the partial pressure of a volatile component of an ideal solution. By now, we know what we mean by the term volatile. We said volatile refers to components of a mixture that easily change to vapor. Meaning that the law only looks at the volatile components of the mixture. And then we are emphasizing that this law is only valid for ideal solutions. If the solution is not ideal, then Raoult's law does not valid. And we have just seen what an ideal solution is. And we are saying is equal to the product. I am saying product refers to multiplication. Equals multiplication. And we are saying the product of vapor pressure of the pure component and the molar fraction of that component in a mixture at a given temperature. So temperature is the condition governing this law. And so mathematically, what can we do to represent this law? We can say that the partial pressure, so partial pressure of a given component, I can say, if we consider here two components, if we consider an ideal solution of components A and B, then by Raoult's law, partial pressure of A should be equal to the molar fraction of A times the vapor pressure of pure A. So we are saying where XA is going to be the mole fraction of A in the mixture. And then partial pressure naught of A is vapor pressure of pure A. That means similarly, partial pressure of B is going to be the mole fraction of B times the vapor pressure of pure B. So once we know these formulae, then we can actually calculate very many things using this law. However, we can remind ourselves from our previous lessons we've had the meaning of mole fraction. What do we mean by mole fraction? You need to know something about mole fraction. Mole fraction, remember that mole fraction of A should be equal to the ratio of the number of moles of A over the total number of moles of the components in the mixture. So Na plus Nb. Similarly, the molar fraction of B should be number of moles of A over the total number of moles of A and total number and moles of B in the mixture. And then the other thing that we also need to look at, is what we call total mole fraction. The total mole fraction for a mixture of A and B must always equal to 1. It's unit. For example, what I'm saying that mole fraction of A, should we add the mole fraction of B, then we shall get 1. Remember, we are saying mole fraction. So we are saying that for mole fraction, the total mole fraction in a mixture of two substances A and B is going to be equal to 1. That means mole fraction of A plus mole fraction of B is equal to 1. The other thing that we also need to know is about total pressure. Total pressure, remember our formula, which is from Raoult's law, partial pressure of A is equal to mole fraction of A times mole fraction of B. But then, what we are interested in is total pressure. Total pressure is the sum of the partial pressure. So, total pressure is going to be equal to partial pressure of A plus partial pressure of B. And so, if that is true, we can even modify this formula by substituting the expression of the partial pressures and say that P total is partial pressure of A, which is mole fraction of A times P naught of A, plus mole fraction of B times P naught of B, such that we have a direct translation of P total representing the real partial pressure of A as it comes from Raoult's law. And then we are saying that these different equations that we see can be used for us to be able to determine different things that can be asked during any calculations. So we have equation 1, which is determining the partial pressure of A. We have equation 2, which is determining the partial pressure of B. And then we have this equation 3, which is determining the total mole fraction. And from this total mole fraction, we can determine many things. For example, if I have been given one mole fraction, for example, I've been given mole fraction of A, I can get the mole fraction of B by simply saying mole fraction of B is equal to 1 minus mole fraction of A. Similarly, mole fraction of A can actually be 1 minus mole fraction of B. So you can see that these expressions can be used to do very many things. We can also now look at this equation 4. So all these equations are used in the calculations that we shall be seeing in lesson 3 about Raoult's law. However, these ones are now the interpretations of what we call the Raoult's law. And every time we are asked about ideal solutions, equation Roman 1, Roman 2, Roman 3, and Roman 4 should be just at our fingertips. And so, in the next lesson, we shall actually be looking at some of the examples of calculations involving Raoult's law. And these equations shall come in and we shall see how we use them. Otherwise, that has been the introduction to ideal solutions and Raoult's law. I said we shouldn't confuse Raoult's law of ideal solutions with Raoult's law of relative lowering of vapor pressure. The other one looks at vapor pressure, but this one is looking at the solution and is targeting the partial pressure of a volatile component. So let's meet in the next lesson for some examples. See you there.